Right before I get into it, so this presentation goes back a few years, but it's never been published, it's never been presented at a major conference, and it kind of, life got in the way, right? But then two things happened. First, nuclear energy is no longer a dirty word, and the world sort of finally woken up to itself, realizing that uranium, if not the solution, has to be part of the solution. That's one thing. And if you don't believe me, I strongly recommend you read that book on the left-hand side there. That should be mandatory reading for any self-serving politician. And the other thing, of course, that happened in that space that you're all aware of is that this guy, and who shall remain nameless, decided to annex Greenland, right? So, and here we are for that exact reason. In addition to all the wonderful sponsors that provide support on a regular basis, RSC, the company I have the pleasure of working for, also sponsored this night's talk. And because of that, I'm allowed to say a few things about RSC. You probably are familiar now or know of the RS and RSC, René Sturck, of course, the guy who founded this company about, 16, 18 years ago, and has since turned it into one of the top 5 geoscience consultancies in the world. And René is well renowned or well known for his, just going to do that, for his contributions to revising the JAWS code and in the QA/QC space and resource auditing and all the rest of it. He's got his own podcast and he publishes regularly on LinkedIn. But RSC is a lot more than just René. So, like I said, we're a big group, and some of them are here. Some of the amazing, bright, super brilliant people that I have the privilege of working with, they are here. And we, like most of these consultancies, we cover the whole gamut in the consultancy space, but we also do collaborative research projects, which is one of the points of difference as far as RSC, with the likes of Geoscience Australia, with MEGWA, for instance. And many people don't know this. We actually have our own in-house SEM facility, which is awesome when you have a client that wants to understand the speciation of their ore mineralogy, or from a metallurgical or processing viewpoint or whatever. And it's often cheaper and quicker than going through university-based equipment. And we basically work all over the world and do really cool and funky stuff. And if it goes outside our core competencies, then we collaborate with the gurus of this world, say, for instance, in the structural space, Brett Davis and the likes. We have, our main office is literally 200 meters that way in Riola Street. We also have 2 offices in New Zealand, and we just opened an office in Riyadh in Saudi Arabia to work. And this is really what you have to have if you want to work with the likes of the ministry, the SGS or Ma'aden and so forth, in the Arabian Shield, which is where the action is. So that's pretty cool. And we also have people in Europe and North America. So yeah, that's us. And with that said, let's make Greenland great again. So why does this guy want to invade Greenland and take on an army of fierce-looking snowmen in the process? It's not because he thinks he can build another golf course there, as the name would imply. It's, of course, about Greenland's vast richness in mineral resources and commodities. And that's why the guy wants to make a deal on his terms. So let's have a look at Greenland, for those of you who might be a little bit less familiar with the place. It's literally the coolest place on Earth. It's the largest island in the world. It's about 1/3 of the size of Australia, but only 20% of that currently are ice-free. But thanks to global warming, that changes every day. The population of the whole of Greenland is akin to the population, I Googled this, of the Adelaide Hills. So it's less than 60,000 people, and of which about 20,000 live in the capital, Nuuk. It belongs to Denmark, as most of you would know, but it's self-governed since, well, for the last 40 years, thereabouts. For the last 500 years or so, main export fishing. And because of where it is, of course, between the world's biggest markets in North America and in Europe, it's in an incredibly wonderful strategic position. And that's another reason why I'm keen on the place. And until about 10 years ago, thereabouts, and as you can see, in 2012, it actually hit the #1 in the Fraser Institute's annual review. because of logistics, infrastructure, perceived zero political risk, and all the rest of it. But for various reasons, some of which you're aware of, that has changed, and I get back to that. Greenland is essentially Western Australia with a 4-kilometer thick ice sheet over the top of it. And if you think about the 1,234 whatever odd mines in Western Australia, it's the same in Greenland, except the mines aren't there yet. But in terms of the commodities that are there and resources, the resource potential, it's just about the same thing. And some of you might have been fortunate enough to attend the annual Greenland Day that GEOS and the Mineral Resources Agency of Greenland put on in the early 2000s here in Perth and in a few other places. They did an amazing job promoting Greenland. And as a result of that, and you can see as per that graph there on the left-hand side, the number of exploration licenses just skyrocketed and went over, exceeded 100 in 2010. And then kind of the bottom fell out. And as a result of that, and at the time, that was sort of the catch cry there, because all of that retreating ice sheet exposed and is still exposing, like, I won't say virgin, but fresh, beautifully polished rocks with stuff sticking out of the ground. Unlike the geological cover-up out here, it's really, really easy to do exploration in Greenland, well, where the ice doesn't get in the way. But then because of that, if you have a look at that, and it's probably a bit too small to read, but just for a point of reference, Australia, as opposed to over 60, a bit over a decade ago, it's down to 3. There's 3 Australian listed companies that are operating in Greenland these days. The other thing that, again, the guy in the White House has his eye on is the immense potential as far as oil and gas surrounding the continental shelf and in the Mesozoic basins around Greenland. Think North Sea, it's exactly the same thing. And so that is another potential game changer, but for environmental reasons and concerns, which is understandable. So what about uranium, I hear you ask? Excellent question. So let me tell you a little bit more about uranium. Like most places after or during the Cold War, there was a fair bit of exploration happening for uranium in Greenland. And so it's nothing new, right? In the 50s for warheads, and then later on when peaceful use of nuclear power came into fashion, vogue, whatever, there was a fair bit of exploration there by the USGS and European counterparts. And you can see from that list quite a range of types of uranium deposits were discovered throughout those times. And of course, most of you would be familiar with Kwanefeld or the Illimorsak complex that's been in the news for all the wrong reasons. Numerous times. But one thing or two things that I want to point out, and remember that, as far as exploration for uranium, nothing north of the 75th parallel and no mention of unconformity-related uranium. Keep that in mind. Right from the start, they imposed a ban on uranium mining, so that didn't help. You can explore for it, but you can't mine it. That was lifted in 2013, did wonders for Greenland Minerals share price. And again, that whole groundswell and everything else as far as exploring and mining in Greenland. However, that got overturned about 4 years ago by a 2-vote margin in the Greenland Parliament. And that's where it's at right now. That hasn't deterred, of course, this guy. And so with that, let's get into the technical part of the actual presentation here. What I'd like to do over the next half an hour thereabouts is give you a brief introduction to unconformity-related uranium for those of you that might be less familiar with the deposit type and why do we care, and then take you through a complete exercise of project and target generation using a mineral systems approach combined with 4D GIS data, in other words, plate reconstruction models, to basically get to where we want to be in that part of the world, and then to top it all off or finish it off, actually go there and ground truth and assess the identified region. And that's kind of what gets me out of bed, or has gotten me out of bed for the last 30 years, really. So why do we care? Unconformity uranium deposits, if we ignore ocean water, and there's a lot of uranium in ocean water, but at low quantities, of course, And if we ignore black shales, like the Alum shale in Sweden, for instance, where we got over 1 million tons of uranium at about 70 ppm, not that great, but that didn't stop the Americans exploring for it by dropping TNT into swamps and then just blowing everything up. And yep, there it is. So if we ignore that, and we also ignore Olympic Dam, freak of nature that Victoria, unlike the Grand Prix, can't take from us, South Australians. It's got about 700 ppm on average, and we've got 1.2 million tons of uranium. It's by far the largest uranium resource, also the world's largest gold and second largest silver resource. But aside from that, if you look at that graph, 3 out of the top 10 uranium deposits, biggest uranium deposits, are unconformity-related uranium deposits. So, and not only are they're big, they are exceptionally high grade. So this graph here is about 300 different types of uranium deposits. All the red ones are unconformity-related deposits, right? So in terms of grade and size, grade is king, size matters. And who wouldn't want to have something like that in their drill core? Close to 25% of uraninite. Beautiful stuff. In terms of the formation, uranium unconformity uranium deposits very quickly, as the name implies, they're in the vicinity of a stratigraphic unconformity between two things: a more or less undeformed blanket of siliciclastic intracratonic porous permeable sediments and a high grade metamorphic basement, usually archean paleoproterozoic, comprising reduced sediments like graphite and reduced sedimentary rocks, and importantly, depending on whom you believe, uranium-enriched potassic calc-alkaline A-type granites with sort of upwards of 12 ppm uranium. Conduits, like with anything, structural conduits, pathways are important, so you have to have that connectivity. And then the unconformity ideally sits there for millions of years. You get a deep weathering profile, which enhances the reducing capability as well as porosity, permeability, reactivity along that unconformity. Like with any hydrothermal system, fluid circulation mixing is key. I don't have time to go into the details of all of that and why there are so-called ingress and egress types and what the actual source of the uranium is. Just briefly, ingress means your deposit extends into the basement for hundreds of meters along structural conduits. Egress means they extend into the cover sequence. So while they are closely spatially associated with the unconformity, they can go up and down for quite some distance, which is why they are called unconformity associated or related systems. Okay, so that's the how. Let's have a look at the why. We covered how and why. Let's have a look at the when, which is also important from a targeting viewpoint, that understanding, right, the concept. If we go back to the Hadean 3 billion years ago, nothing much going on. You had a ball of magma covered by a thin crust of lava and an oxic atmosphere, and the uranium was just happily floating around in the magma. No way could you form a deposit then. But then plate tectonics kicked in, and as a result of that, all these incompatible elements, including uranium, get successively enriched in the increasingly differentiated, fractionated felsic upper crust, and through uplift, erosion, deposition in intercratonic basins. That's the first peak of uranium deposit formation in Earth's history. And of course, all of that is kind of related to things like the Witwatersrand, because the atmosphere was still anoxic. Can't form an unconformity-related deposit in those circumstances, right? But then another thing happened, the great oxidation event. Atmosphere turns oxidized, and as a result of that, all the accumulated deuterium starts to dissolve and gets sequestered into reduced sediments, and actually has the opportunity to accumulate along these redox boundaries, including unconformities that I mentioned earlier. And that is the peak of unconformity-related uranium mineralization in the Earth's history. The third peak, incidentally, and fourth, that's related to sandstone-hosted roll front deposits. They're all much younger, right? But this is when it was all happening. And on top of that, that was also the time when the second supercontinent in the Earth's history formed, Nuna, which again gave rise to these massive intercratonic stable platforms into which you could deposit all of this detritus and then form your unconformity systems along these things that I explained earlier, right? So that's worth keeping in mind. And because of that, all of the world's largest and highest grade unconformity associated uranium deposits are essentially between 1.55 and 1.8 roughly billion years old. No way around it, okay? Okay, so we have the how, where, and when kind of sorted. And the brief now then is using a mineral systems approach and looking at source, transport, and trap regions, target areas of unconformity-related uranium deposits. Critical for these things from a mineral systems viewpoint, as I said, so you've got your basin, you got the unconformity in between. So that could be one of the sources if you believe like second cycle enrichment of uranium in the basin, or it could have come from the high-grade uranium enriched A-type granite kind of thing basement. It doesn't really matter. Connectivity between these things by way of these big shear zones, and then of course the trap along or within close proximity of the unconformity. And all of that essentially leads us to the Athabasca Basin template. So whatever it is that you're looking for in a frontier region that hasn't been explored systematically, it's got to basically tick all those boxes that the Athabasca Basin ticks. And the Pine Creek to some extent, and a few other less well-endowed basins. So what is the Athabasca Basin template? It's this, in that most of you would be familiar with where the Athabasca Basin is, and keeping in mind that this is a remnant basin. Hundreds of million years, 1.5 billion years ago, it was connected to what is now the Thelon Basin, another remnant basin, the Amundsen Basin, and a few others that aren't labeled here. But so unlike the Thelon, where you have Kigavik and a few other decent-sized unconformity-related systems, nothing up there, the Athabasca Basin, that's what it looks like in cross-section. You've seen this before. The world's largest and highest grade unconformity deposits are all in the, as far as we know anyway, in the eastern, southeastern part of the Athabasca Basin. Why is that? Well, for one thing, there are two cratons, the Hearn and the Ray, that came together during the formation of Laurentia, that then became part of Nuna. And they came together during the Trans-Hudson orogeny at around 1.8, 1.5 billion years ago. So what you're looking at here, the snowbird tectonic zone, is a 2,800 kilometer long terrain bounding suture. It's a mantle tapping structure. And they are second order, but they're still transcrustal faults. Second order structures like the Clearwater, the Cable Bay, or the Virgin River shear zone. They are all running along here parallel to the snowbird tectonic zone. And all these big deposits are associated with these things down to 1,000 meter present day. But you also got to keep in mind, because this is a remnant basin, there are lots of uranium, unconformity uranium system outside of the present day erosional level, because you're really only a few meters below the eroded unconformity. And again, if you think back to this, there is absolutely no reason why you can't find big systems along here or down here. And in fact, they exist and they have been found. But all of this is covered by up to 10, 15, 20 meters of till, glacial deposits, which makes it very difficult. And exploration within the Athabasca is all geophysical. And it's flat as a pancake. Okay, so here we are with our approach and methodology sorted. We turn to the GIS-based plate reconstruction models that we use in order to identify the frontier region. Spoiler alert, it's northwestern Greenland, as you know. But how do we end up there? By, in the first instance, using G-plates, which is an ArcGIS-based or web-based, Python also scripted thing that you can use. It's freely available, and you can move around these 678 polygons, and this thing keeps growing, and do your own thing that I'll get to in a minute. The starting point are paleomagnetic data points, of course, and that's been happening for the last 20 years or so, and it also incorporates aspects of lithology, mineral deposits, and all the rest of it, which then ties in with the STRAT database and the geochronological database that Bruce Eglinton at the University of Saskatchewan's managed. And I acknowledge this name in the title of the whole thing because that's his contribution to all of this. And this keeps growing, right? This keeps getting better and more refined, and it's a brilliant tool. How does it work? I'll just take you through 400 million years of Earth history to basically get to where I want us to get. So here we are 2 billion years ago. You can kind of make out the bits and pieces that will all come together in the next 100 million years to start forming Laurentia, and then all of this ends up coming together to form Nuna. The Hearn and Ray craton are already in close proximity of each other. So the Trans-Hudson orogeny is essentially these two things coming together over the next 200 million years. And our target area essentially, and I want you to keep an eye on that when I play this in a second, that's basically Proto-Greenland, that's the north, that's the southern part of Greenland. And it's got a point because by that stage, Greenland was definitely part of what then ends up being North America. So you'll see these things moving around and notice that this part of Greenland sits on the equator based on paleomagnetic data. And that's important because you want your intercratonic basin in a low latitude environment. You don't want to be where it is right now. Not good. Greenland, that is. All right. So as this counts backwards, there'll be things popping up that are uranium age dates for places like Jabiluka and Kungara over here, because that's the North Australian craton there, moving around, also staying at low latitude. There's Greenland forming at about 1800 coming together. That's Laurentia, the Trans-Hudson. And then there's the Athabasca Basin popping up now, the start of the intercratonic basins. That just over here, that's Australia, Ranger, the age for Ranger. And then you see the yellow dots there. That's the basins that I pointed out earlier. And then it's all coming together. Boom, here we are. Now we've got Nuna, the whole thing, Laurentia forming part of the supercontinent. The area outlined in red is kind of the inferred extent of this massive intercratonic basin that the Athabasca, the Thelon, the Amundsen, the Borden, the Fury, Hecla, and all these other remnant basins were part of. Perfect conditions for the formation of unconformity-related uranium. And of course, what I'm getting at here is that's our target area, right? Everybody explored these things. No one's done any work down here, though. That's our frontier region. And so let's have a closer look at that and test that notion and drill down, pardon the pun, into the veracity of that hypothesis. So down here is the Ray and the Hearn. There's the snowbird tectonic zone coming up, running into Baffin Island, and then hypothetically extending into Greenland. And unlike the Yilgarn or Western Australia, that's the extent of what we know in terms of the interior makeup of Greenland because of the 4 kilometers of ice over the top, which essentially causes the crust to go down to over 1 kilometer below sea level in that part of the world. So the area around the coast obviously been mapped reasonably well. And because of that, we know that the Thule Basin in northwestern Greenland comprises two things: high-grade Archean basement and a mid-Mesozoic siliciclastic intercratonic sedimentary cover. Perfect. Then if we put all that together and have a look at these remnant basins extending from the Athabasca up into essentially Greenland across Baffin Bay, you notice that all the yellow stuff here is essentially siliciclastic sandstone, siltstones, kilometers of it, intercalated with various amounts of shaly aquitards, and in some instances, these green bits, basalts. And bear that in mind because they're important. Okay, so that still makes a lot of sense. Excuse me. Okay, and with that in mind, so let's jump across to Greenland. No longer part of the USA, but it's clear that, again, if you look at all of this, it ticks all the boxes. We have a thick, undeformed, presumably Mesoproterozoic sedimentary succession. It has to be at least 5 to 6, 7 kilometers in thickness in order to get the hydrothermal fluid flow get it going. We have basal sandstone units, and I'll get back to that. As I mentioned earlier, low paleo latitude, perfect. It's a continental shallow marine, intercratonic, what have you, sequence overlying this high-grade basement. And most importantly, from our targeting exploration model viewpoint, it's a frontier region, has not been explored for uranium or anything else for that matter before. Okay, next step, ground truthing. So rather than just going over there and seeing what we find, we correlated all the different key sites along the coast that Peter Dorst put together on the 2 occasions when he did mapping for GEOS, the Danish Geological Survey, in that part of the world. He produced a couple of 1 to 500,000 maps. That's it. It's the only person really who spent a bit more time up there looking at these things. So we pulled these together on the basis of that, established the sort of guesstimated approximate extent of the Tule Basin margin. And then on the basis of that, selected about 10 key sites that we wanted to check out. And that dashed line there, that's sort of the extent of the ice-free zone along the coast. So there's no point in going any further inland, of course. And based on that, we kind of estimated that that's the approximate extent of the central part of the Tule Basin, where you want to be and where you'd expect to see evidence of that unconformity surface. And one thing that I just point out quickly here is this area outside the sort of guesstimated extent of the Tule Basin. Keep that in mind. Okay, so with all of that, we packed our bags or backpacks, and as far as being based in Adelaide, 8 easy steps from Adelaide to Melbourne, from Melbourne to Hong Kong, Hong Kong to Paris, Paris to Copenhagen, which is where Air Greenland departs from, across to via sort of Iceland under the clouds to Kangerlussuaq, which is the international airport in the southwestern part inland in Greenland. From there, you jump on a smaller plane and go up to Ilulissat, which is the hub on the west coast. Cruise ships go there every now and then. Try not to pretend they're the Titanic. And from there, you catch another flight up to Upernavik on the west coast via Thule Air Base. No photographs, not allowed, to Qaanaaq. That's where you basically want to be. Qaanaaq is a seasonally populated town with one road in and one road out as far as the airport, which is a gravel airport, 1 flight a week. So if you want to go up there early, and it's, as I said, 600 people mostly fishing in the fjord there. The only way to get around really is by helicopter. And when you do that, you really see the kind of effects of global warming in your face. And you also can look across to Canada there, Ellesmere Island. Another thing that's really cool, obviously, pardon the pun, geology in your face. It's absolutely spectacular. And another thing that's great when you're up there in summer, of course, is the midnight sun. This is us coming back from the field at 1:45. That's not AM, that's PM. The sun basically does this over your head, right, during summer. But before you go out, before you're allowed to go out, you got to do this, safety training. So I had to demonstrate that I was capable of firing off a double-barreled shotgun. I did my national service back in the day, so kind of familiar with these things. Still, it's got a kick. And the reason for that is the polar bears around, right? So when you're out there, you always walk around like Dirty Harry style with your gun over like this, and you constantly check for polar bears. And most of the time we're away from the coast, so polar bears they can't be asked walking up these things, but they're there. And while we were there, a lady over in Ellesmere Island got mauled by the polar bear. So that really drove it home. But, and the other thing with this is, of course, when this 2-ton animal charges, and you got to wait and wait and wait until you actually can make sure you hit it between the eyes. By that stage, it's too late. So our friend from GEOS, he's got the Dirty Harry style Smith & Wesson there to really kind of, as a backup. But for me, it was really important knowing that I could run faster than either of these guys. And with all of that, it was time to check out the first of our selected key sites in the field. And this is one of those examples where we are looking across from the southeast to the northwest, across the Robertson Fort, which is to the east of Quanaq. And not sure whether it's a bit washed out, but I'm sure you can hopefully can see it. So there's the unconformity, that's the dark gray, greenish, high-grade metamorphic basement. And all of this is about 1.2 kilometer in vertical elevation. That's the mid-Proterozoic sedimentary siliciclastic sequence with the various formations. And there's a basaltic sill coming through. That's what it looks like in close-up. So the whole it's been tilted a little bit, but there's the basaltic sill. It's about 70 meters true thickness. But the other thing that you get really excited about when you're there is this is the high-grade metamorphic basement. There's your graphite-bearing pelitic schist, exactly what you want to see. And above the unconformity, there's your cross-bedded, immature, archosic red bed sediment. Perfect. A couple of other locations further to the east, Bowdoin Fjord, both sides. So that's there. There's these two rectangles. This is looking across to the eastern side. That's in the opposite direction, looking or standing on the unconformity on the western side, and it's in your face, right? There's the high-grade metamorphic basement. There's your red bed sequence. That's my colleague Jean-Luc putting his hammer literally on the unconformity surface. You can't do that in the Athabasca Basin or in the Thelon Basin or even the Pine Creek for that matter. This is just so instructive and in your face. It's bloody brilliant. And here there's shown again, there's a 500-meter drop down to the ocean and an 800-meter vertical cliff back up. There's a basaltic dike again, Clarence Head, Northumberland. There's the unconformity. I mean, even Blind Freddy couldn't miss that. And the bleached, cross-bedded red bed sequence, which incredibly immature material across. That Cape Trout wine here is down here, by the way. And Quanaq for reference is there. And one more slide to bore you with, and the unconformity on Wolstenmont Island, there it is again, dark green, red, can't miss it. Beautiful polymictic arcosy. And then we were down flying along here, looking for further outcrop and evidence, and we saw this in the distance, this 1.5 kilometer high here cliff. All green, dark stuff, and then this really light colored stuff on top. So we landed a helicopter up there, and lo and behold, there it is. Deeply weathered, unconformity, paleosurface, massive conglomeratic, cross-bedded, red bed sequence above, looking like this in close-up, and again, this sort of thing. And that's the deeply weathered paleosurface underneath with the chloride, the kaolinite, the smectite. Exactly what you want to see. It's just really, really cool. And the high-grade pelitic, graphitic material right underneath that. It doesn't get any better than that. And okay, I mean, I could bore you silly with thousands of photos like that, but we'll leave it at that because now we get to the point where, okay, we've seen all this, we've done our measurements, our reconnaissance assessment. How does it hold up in the final analysis? And as you can see from this bullet point list there, it ticks pretty much all the boxes in terms of the age, the makeup of the basement and the cover, the presence of graphitic material, some of them with pyrite in them, beautiful fresh pyrite in the basement, got metamorphosed during the Trans-Hudson orogeny, and then you had uplift, penetration, and the deposition of the Tule Basin, 5, 6, 7 kilometers of it. It's an intercratonic basin. You've got the unconformity, and we took some samples and analyses, and we got up to 18 ppm of uranium in stream sediments, and up to 400 counts per second, the gamma ray scintillometer, which equates to about 30 ppm uranium in the basement, which is pretty damn good. You've got these big structures going through. It extends across the Baffin Bay into Canada. So brilliant. And you've got 100% outcrop over about 80,000 square kilometers. There's a lot you can do with that. You can also hide a lot of unconformity-related deposits in that. It's not all sunshine and wonderful, though, because there's quite a few cons as well to consider. Some of them are, or we would consider, not fatal flaws or even red flags. It's simply because of the poorly constrained geology, the very limited age dating, one age date from one of the basaltic sills. And that's why we know that the minimum age is 1270, which is kind of what you want, right? That's the only age from that entire part of the world. Not a single drill hole, of course. And as I mentioned earlier, 1 to 500,000 maps, extremely limited maps, no GIS data whatsoever. So extremely low data density, no radiometrics, no airborne or ground geophysics, absolutely nothing. But then when it gets a little bit more serious is the basalts that I mentioned earlier. And you remember you've got that 1.2 kilometer high of vertical exposure, and quite close to the bottom of all of that, or the base, you've got these basaltic sills, and they're essentially aquitards. And unlike the Athabasca Basin, where this whole bowl was had free-flowing hydrothermal fluids going through it, leaching uranium, bringing it in contact with structures and depositing the good stuff along the unconformity, that is not likely to have happened there because of the presence of these basaltic sills. How extensive they are, we don't know. And how much that would have affected basin-wide fluid flow, we don't know either. But that's something that is a red flag, right, to me. In addition, there's a lot of, this is textbook faulting, both normal and reverse, along these half-graben structures that got reactivated and pushed back up. And a lot of these faults, they're fresh. There's no hydrothermal alteration or evidence for major fluid flow going through them. And that is a red flag. And the other thing, that this block faulting and half-graben structuring caused most likely is a further compartmentalization of the basin, further restricting basin-wide fluid flow. So your hydrothermal fluid cells would have been quite restricted and small. But again, a lot of that is still to do with the fact that the data density is so incredibly low and limited exposure, all the rest of it. Again, global warming contributes or helps with that. And also, I mentioned, yes, we collected samples up to 18 ppm, and we got 30 ppm in basement, but in a lot of other places, those granites and pegmatites, they were dead as a doornail, less than crustal average. So is it a mineral systems failure, or is it still too early to tell? And that's basically an open question that needs more work. And as a consequence of that, there's a few recommendations that came out of this, and stating the obvious in terms of age constraints, isotopic data, airborne surveys, more systematic stream and lake sediment geochemistry and all the rest of it, and more in-depth analysis, because we were there for 16 days. 3 of those we couldn't fly because it was pissing down. So it was a reconnaissance trip and testing a target region, a frontier environment. And I personally haven't given up on it, but of course, because of what's happening in terms of the uranium ban, it's not exactly something that would cause people to rush out and do more exploration. And just another plug for G-plates. As I said, it's a fantastic tool, and you can do that sort of stuff that we did and what we applied it to for obviously anything and everything. And that's really cool. But either way, you need to have a conceptual targeting model, a clear idea of what it is that you're after, and ground truthing. Again, stating the obvious, absolutely essential. Early stage, and not kind of sit on that for too long before you go down a rabbit hole and waste money on everything. But something really good came out of it, in that it contributed to a workshop entitled Assessment of the Uranium Potential in Greenland, modeled on the USGS 3-part assessment of undiscovered resources, porphyries, and various other things all around the world that I'm sure you're familiar with. And you notice that not only did unconformity-related uranium mineralization make the list, so that's this table here summarizes that. There's a whole bunch, not just the Tula Basin, but a whole bunch of other regions that have been identified as being potentially prospective for unconformity-related uranium in Greenland. And there was a consensus that there's a 50% chance of at least 2 unconformity-related deposits being found in the Thule Basin. So, yay. And with that, I'll thank you for your attention. And if there are any questions or you want to raise anything, yeah, more than happy to answer them if I can. Thanks.